Okay, so the video today kind of expands a couple previous videos in the playlist. We talked about intra-device communication between components in our device, and there was something mentioned in there. We're going to go ahead and see it today. And there's another video in the playlist where we talked about how we combine logic gates up to form and store a bit, a single bit of memory. And a single bit of memory is not much. We're not going to do much with a single bit. So typically we would combine lots of those together, lots of those latches or flip-flops together into a memory device. So that's our topic for today. Random access memory, which is basically lots of flip-flops put together. A big conglomeration of those flip-flops or latches that store a single bit of memory so that we have enough to work with. So let's talk about this a little. Okay, so to clarify a point I just made and introduce some technical terms, we have more than one type of memory. I'm just going to list the two most popular ones here. We have dynamic RAM, which you'll often just see listed as DRAM. And this uses a capacitor and transistor. Capacitor and transistor to store. So it stores a bit using a capacitor and transistor. The other most popular one will be static RAM. Static RAM, which you're going to hear referred to as SRAM. And this one uses flip-flops. Flip-flop to store. So obviously, since the video about memory went over flip-flops, this is the one we're going to talk about today. But there's more than one type of RAM, more than one way to store a bit. These are probably the two most popular, nowhere near an exhaustive list. DRAM is a little bit cheaper. So especially when you get up to a machine with lots and lots and lots of RAM, you're probably going to see DRAM because those costs add up. But this stuff happens in the background, and once the components are hooked up, we interact with them in basically the same way. Might as well mention it. The chip I'm going to use today, the ones I like to use with microcontrollers. So microcontrollers are primarily a read-only memory thing because that's for a specific purpose device. So we know what it's going to do every time. So we use a lot more read-only memory than random access memory. But when I need a little bit more, they don't have much in there. So if I need a little bit more, I like to use these chips called 23K256, which have 256 kilobytes, bytes being 8 bits of SRAM. And we can use more than one together, so if I have a project that suddenly needs a lot of RAM and I need a gig of RAM, I can just use 4 of these chips and get a gig really quick. Or however many, tie a bunch of them together, the little bitty things, so they don't take up much space. But a little bit more RAM than a microcontroller offers on its own, and it'll work for the example to kind of go over what RAM is. And there are different types of RAM. These are probably the two most popular. We're going to cover this because obviously that's what we went over in the video memory, but there's lots and lots of ways to store a bit of memory. And then when we put lots of those together, that's where we get to RAM and ROM. So what we're going to think about with RAM is this is an analogy, not exact here. We can just think of a big grid of those flip-flops. Well, with SRAM, where we're DRAM, a big grid of the things we have. Okay. Some big grid of bits. And it's not exactly a super nice organized grid because there is an issue that occurs when we put things together. Remember, we're combining transistors or MOSFETs together, which each have, I'll use a MOSFET as source, a gate, and a drain. So if we have several of them together, we can inadvertently create an extra one in between it because maybe, we have a source, gate, and drain from different MOSFETs too close together and inadvertently create another MOSFET in between them. That's called a phantom transistor. So then that's a big issue, getting into complicated electrical engineering, but that can also be taken advantage of, right? If we're having trouble positioning it, then maybe those three we could add a fourth use in between. If we can find some that are never going to be used at the same time, go ahead and use that phantom one as well. But that's getting very complicated, and that's super advanced. Usually we avoid phantom transistors, so it's a puzzle organizing all those flip-flops in there so that we don't end up with any phantom transistors. But unless you're designing a chip, just think of it as a big grid of bits. All right? Bunch of bits in there. And then it's organized. That grid, think of it like a grid, a table that is staying like it is. So our CPU, or the control unit for our CPU, knows exactly where everything is, and it can ask for it. And there's different ways that it can ask for it, right? We can ask for a single bit at a time. And I'm using the term ask to go both ways. We could ask to write a bit, or we could ask to read a bit. So I'm going to use that word, say ask, for interacting. A single bit at a time. That's why we were talking about this, because 1 bit at a time is not much. So then we can increase that to a byte, which you're probably familiar with is 8 bits. But then we can keep expanding that out. And there's some other ones that you would have seen in your textbook that I want to clarify here. So the next one is a word, which is a combination of bytes. And in your textbook, or a textbook, or some sort of online reference material, you probably saw it listed out with a certain number of bytes or a certain number of bits make a word. This one changes. So what the textbook or online reference material said is probably the most common for the time it was written. Hopefully you're using modern reference, so it's the most common for this. But a word is really going to be your register size. So if you have 16-bit registers, there's 2 bytes in a word. And if you have 32-bit registers, there's going to be 4 bytes in a word. A 64-bit machine, when we say that, we're referring to the register size. So on a 64-bit machine, we're going to have 8 bytes in a word, or 64 bits in a word. So that one changes. And the term we'll often use when interacting with RAM is also page. That one probably wasn't listed in your textbook. But a page is kind of all of your registers. So typically the standard setup is square, so a very common one would be 32-bit registers. So it kind of squares out. But a page is all of your registers. So if we ask for a page, if we want to read a page of data from the RAM, that means enough bits to fill all of our registers at once. And we can also retrieve the entire contents of RAM at once. That one is usually avoided. We're able to, but remember, that's going to take a while. That's going to take time, so if you have to, you might want to sit down with the calculator and make sure you know how long that's going to take, because it can really slow things down. There's some different ways we can retrieve it. We can read and write, ask to interact with it, 1 bit at a time, 1 byte at a time, 1 word at a time, which basically means the contents of an entire register are coming and going at once, or a page at a time, which means the contents of all our registers are coming and going at once. and then everything. But that one is usually avoided. Uh, it takes time. It slows everything down. So typically, if we have to do that, we try to find ways around it. Read a quarter of it, start doing stuff, then go back and read the next quarter of it, and kind of break it down or something. But that's kind of the ways we can interact with it, and just think of it as a big grid of bits, and it does not change. So our control unit in the CPU knows exactly where each one is. Each one has an address. We can ask for bit 1, bit 2, bit 3, bit 4, and so on, to however many it is. And then we can organize that. So if we're saying bytes, bit 1, the first bit starts our first byte. Then bit 8 the 8th bit would start our second byte, and so on and so on. Same thing with words and pages. The CPU knows exactly where everything is because it's not changing once it's put there. And that's kind of what RAM is. And the other thing is it does not stick around. So memory is temporary. When we shut off power to the machine, what's in RAM is gone. So it's not a long-lasting storage. It's the working storage. And the trade-off for that is it's a whole lot quicker than storage. So we could store stuff in RAM, or we could store stuff on SD card and make it interact the same. But if we put timers on it, we would notice a big difference because it can get it from RAM a whole lot quicker than it can get it from like actual storage. Memory is quicker than storage, but memory doesn't stick around. When we shut off the machine, the memory is going to be empty. That's kind of the difference. So, but just think of a big grid of bits. We know where every bit in there is, so we can access it as needed. And that's kind of the gist of what RAM is. Let's look at an example of just plugging one up. It's a short video, so yeah, just kind of the basics of RAM here. So we'll plug one up and modify an example so that it's happening in the foreground instead of the background to see what's going on with it. Okay, so I was getting ready to hook everything up here. Got the RAM chip for the example here. Pulled out the microcontroller, and something that hasn't been expressed anywhere that I thought I would share is, well, I have lots of microcontrollers. So I have no idea what I was doing the last time I used this particular microcontroller. So I don't want to inadvertently send a signal to the chip when it first starts up. So obviously it's going to have the power off when I hook everything up. But another thing I like to do over here on the computer, I have a completely blank sketch. So before I hook anything up, I always like to upload a completely blank sketch, which obviously there's nothing there, so it doesn't take very long. But that way I know the microcontroller is not doing anything. So when I get everything hooked up and apply power for the first time, I don't have to worry about something unexpected happening. Just a little point I thought I would express there. So this video doesn't seem to be taking too long, so I thought I'd work this in here. This is something that's happened a lot in the playlist and not been discussed with hooking up the circuits. But the chip is going to operate off 3.3 volts. Somewhere between 2.6 and 4.1 volts is the range we can use with this chip. But the Arduino, while it does have a 3.3 volt supply that we can send to a power rail, the pins for controlling things all operate with 5 volts. So I need to cut some of that voltage out. And we do that with what's called a voltage divider. And the idea is from whatever voltage we initially have, we send it through a couple resistors, and by the time it gets back to ground, all the voltage has been eaten up. So like here on the meter we can see 4.5 something volts, somewhere in that range. And by the time it gets back to the ground rail, it's at 0. So different size resistors will burn up different amounts on the way through. So here I have a 2200 ohm resistor burning up some of that voltage. Then it goes through a 4700 ohm resistor to burn up the rest of the voltage. And right in between them is the range I'm looking for. So 3.15 volts. That'll work perfect for the chip. So just a voltage divider. It often happens with microcontrollers, we need to turn 5 volts into the 5 volt range into the 3.3 volt range. And a quick voltage divider to get that is going to be a 2.2 kilo ohm resistor followed by a 4.7 kilo ohm resistor. And that just adjusts the voltage to the level we need. Okay, so here's that chip in action. Obviously RAM's happening in the background, so there's not a lot to see here, but here's what it looks like hooked up. I usually hook up SPI communication to these buses. So I just have the SPI communication controlling the RAM, all the power, a bunch of voltage dividers to get everything from 5 volts to 3.3 volts. And again, RAM usually happens in the background, so had to move to the foreground in order to see something. Let's go look at the code running and kind of see something from this RAM. Okay, so this varies from the examples in the playlist a little, because obviously normally RAM is something that happens in the background, but we can move it to the foreground and take direct control over it. So I just went on and found a popular library that's written for Arduinos that does it in the foreground. That way there's something to see here. And this is the example for how to use it that came with the library. And all they're doing is they just write some stuff to the chip. So, and that's basically what it is. We can write to the chip or read to the chip. Write to RAM or read from RAM. And here they're just doing that with a couple of delays and then printing stuff on the serial monitor. So if I open the serial monitor, it kind of looks like this. So they wrote a digit in there. You can see the blocks of memory. Some of they're emptying out, filling back up, and changing with these different things. So nothing really spectacular to see here, but you can see it's empty blocks of memory that are periodically being cleared out and replaced, and that's kind of what RAM is. There's not a lot to see. It happens in the background, but we can see things going in and out this way at least. So to wrap things up here, kind of the key point about RAM and the point of looking at that example is there's nothing to see. We can't see it, so we have to when we're working with it, we have to try and visualize what's going on, find a way to visualize it. Right? It's a big grid of bits, think of it that way. CPU knows where everything is. It's mapped out. Well, a grid, like a city. So we could just think of each little block in memory as a house for our bit. So a 1 lives there, and a 0 lives over there. And like in a city, those houses have addresses. It can refer to each one individually. Then bytes, I didn't count anything when I drew the grid, but I'll put to 1101. So maybe think of a byte like roommates in a house, a bigger house where there's some roommates there. And maybe a word, 110101. I didn't count the grid, so I'm just drawing a bunch here. Whatever the word size is, think of that as like an apartment, an apartment building, a whole bunch of them. But yeah, an apartment building in a city on a map is going to have an address, so we can look at a map and know exactly where that apartment building is, or exactly where a particular house is in the city. And same thing for our CPU. These are like little houses and apartments for our bits. So the CPU knows exactly where each bit lives. One way to think about it, hopefully that cleared up a little bit of the mystery. It is kind of a mysterious point because the whole reason for that example was to actually see that there's nothing to see. We have to visualize it. We have to visualize it internally when we're working with it. Try to come up with something that works to picture what's going on because, we're looking at a little integrated circuit that's doing stuff in the background, so we can't CC stuff happening there. But you want to come up with some sort of analogy that works with your mind in case you're working with RAM to keep track of everything. Hopefully that helped clear up a little bit about what it was. Just a big grid of numbers, and they're temporary. They go away when the computer or when the machine shuts off. But it's quicker than the storage that would stick around. So the quickly accessed ones. And for RAM, randomly accessed, we don't have to go in order from beginning to end. We can just jump to a particular address and then use those bits. That's the random access. Hopefully that cleared that up a little bit.